All right, so today we're going to take a look at graphing sections, or graphing rational functions in section 4.2. We'll split the section into 2 days. So we're still going to have to find asymptotes. That's going to be like the big thing for today. How do we find horizontals? How do we find verticals? Things like that. So remember, not every time the denominator is 0 results in a vertical asymptote. What is the other thing that can happen? And I'm kind of mentioning it here, but what can happen besides a vertical asymptote? You can get something in the graph, you can't even see it because it's so small. Remember? Yep. A hole. And do you remember when we get a hole? If the numerator and denominator have, yeah.
Common factors.
Yeah, common factors. It's right up there. So if the numerator and denominator have a common factor, that's when you get a hole in the graph. So let's take a look at an example. And hopefully everyone can look at that pretty quick and tell me the value you cannot use for x. What's the value you can't use for x? 1. Now the question would be, all right, is it a hole at 1 or is it an asymptote? Well, I see a common factor. The top is x minus 1, the bottom is x minus 1. Let's graph it and see. So we've got x minus 1 divided by x minus 1. We're basically dividing two things that are the same. X minus 1 divided by x minus 1. When you divide two things that are the same, what do you always get? 1. So this is basically going to look like this. In fact, visually, you're not going to be able to tell the difference between the horizontal line at 1 and graphing that. Okay, so let me graph it. Let me change my window. Let's do zoom 6. It looks like the line y equals 1. But there is a hole in the graph. All right, so what I would do if I was going to sketch it, kind of exaggerate it a little bit and just show that there's a hole right there. By looking at it, you'd never know there's a hole. The only way you would know is if you went to the table and you happened to try different values to see what you get, and all of a sudden you try 1 and you say, oh, man, that 1 is an error because you're dividing by 0. So you never really know looking at the graph. You only know looking at the original formula. How about this one? Hole in the graph or vertical asymptote? Yeah?
Vertical.
Okay, how come you think it's not a hole?
Just because of the square, because it'll turn it into a...
So if we write that out, think of it as x minus 1 times x minus 1, right? That's what x minus 1 squared means. Over x minus 1. Do the top and bottom have any common factors? Yeah, what's the common factor? X minus 1. So because they have a common factor, we're going to get that situation where we might not notice it on the calculator. That means it's a small hole again. Right. So if I change it to just putting in an exponent of 2, second insert squared, it's basically going to look like the line y equals x minus 1. Okay. Think of it this way. One of them cancels out, and you get y equals x minus 1. Slope 1, y-intercept negative 1. Can't even tell there's a hole in it. Unless you try to trace to 1, and you notice there's no y value. You can go very close. You can go 1.01. That's good. You can go negative. You can go 0.99 or 0.999. You can get very, 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 very close to 1. You just can't type in 1. So again, we have a small hole in the graph, which means it's not continuous. If you were going to draw that, you would have to pick up your pencil at the hole and then put it back down. So I've been calling it a hole, but what it's really called is a removable discontinuity. Removable means it's kind of a small problem. We could take care of it. Right? All we'd have to do is fill in that little hole, and then it would be continuous. A vertical asymptote is not a removable discontinuity. If you've got a graph that looks like this, that's a pretty big problem if you want to draw it connected. You wouldn't have to just change one little dot. You'd have to change the whole look of the thing. Okay? So removable discontinuity means it's an easy fix. You could fill in that little dot, and then it would look connected. Vertical asymptote, there's no easy fix to make that look connected. I'd have to change the look of the whole thing. All right. And if I take this last problem and just change one number, now the top and bottom don't have a common factor. So what's going to happen now is I'm going to get a vertical asymptote. Right? Just by changing that one number, I don't get a hole in the graph anymore. That's one we're going to look more at tomorrow. That's called the, no, actually, we're going to get to that today. So I'll tell you what that's called later on. So there's an asymptote here. There is a vertical. There's no horizontal in this one. Okay? There's kind of an asymptote going this way. We'll talk more about what that's called later. You know what? Actually, we're not. I don't know if we're going to get to that one today. I can't remember if we get to it. We don't get to it today. We get to it tomorrow. So this is just an example of a polynomial. What would an actual problem look like? Something like that. You've just got a polynomial in the top, polynomial in the bottom. We try to write it so the exponents get smaller, and you end with the constant. Like 5x cubed plus 3x squared minus 8x plus 6. Okay, something like that. Now, does anybody remember what term in the top? There's a bunch of terms, right? But there's only one term here in the top that's really going to control everything that happens. Does anyone remember which term controls what the whole thing is going to look like? The other terms might cause like little twists and turns. The first one. Because it has the highest power, right? So we called that, does anyone remember what this stood for? We called that the EBM, stands for something. So we're looking at what's happening on the extreme left and right, what do we call those? Left and the right sides of the function. We don't call them the sides, we call them what's happening on the...
End behavior model.
Yeah, the ends. We look at what's happening at the end, so the end behavior model. So this is the end behavior model for the top. And likewise, if you wanted to know the end behavior model for just the bottom, it again is the highest degree term. So we have an end behavior model for the top. That predicts what the top is going to look like. We have the end behavior model for the bottom. That predicts what that's going to look like. If we wanted the end behavior model for this whole thing, what do you think we would do with the one in the top and the one in the bottom? Well, what's the operation we're doing here? Dividing, right? We have something in the top, something in the bottom. So we would take these and divide them. Now, subtraction is going to be involved, but I'm not sure if you were thinking exactly the thing I'm going to show you about subtraction. Maybe you were. I'm not sure. But that's the key. We divide them. So this function, f of x, whatever it is, as x gets really, really big, basically, that's what you're going to get. Okay? If you're saying, well, what about all the other stuff? What about all those other terms? Don't they make a difference? Not really. If x is in the millions or billions, they don't really matter. If x is small, like if you plug in, like if we look at this one, and you say, well, what if you plug in 1 for x, or 2, right, and get the answer? And then I say, well, just plug in 1 for the first term, plug in 1 for that term, and just divide that. Are you going to get a different answer for a small value for x? Yeah, it's not going to come out exactly the same. But if x was in the millions, think about if you square a million, double it, and subtract 1. What big deal does it make if you already have a million squared, doubled, and then subtract 1 from it? It's basically insignificant. Subtracting 1 doesn't even matter. Same thing here. You might think, oh, what about if you plug in a million for x and double it? That's plus 2 million and 1. Plus 2 million and 1 is so small. If you take a million and cube it, and then triple that, that's huge. Adding 2 million and 1 doesn't even make a difference, because you've already got something here that's in like the trillions. So a million compared to a trillion, it's very, very small. It's like comparing 1 to 1,000. Very, very small. All right, so this end behavior model predicts what's going to happen in our rational function. Predicts what's going to happen as we head towards the ends of the function. It does not give you a prediction of what it's going to look like in the middle. End behavior model. Ends. Okay? As you head really far to the right or really far to the left. And what do we call that? As x heads really far to the right, we say x is approaching what? Infinity. What about as x heads really far to the left? Negative infinity. So that's when you use this. Big numbers for x. And I told you subtraction would be involved because what you're going to end up with is you're going to end up with a number here and a number here. All you do is divide those. Whatever a sub n and b sub n is. Well, if you had something like x cubed divided by x to the first, remember the way you divide things with the same base is to subtract your exponents. So x cubed divided by x to the first is x to the 3 minus 1, or x squared. So any questions on that? So that's how you find an EDM for a rational function. Just take the biggest term in the top, highest degree term, and divide by the highest degree term in the bottom. So let's go back to this. So this says to find the end behavior model, and then use the end behavior model to find horizontal asymptotes. Because remember, asymptotes are what happens very, very far away from the origin. This model is going to tell you exactly what happens very far away from the origin, towards infinity. All right, so let's just look at it. And I kind of already did it, but what's the highest degree term in the top? 2x squared. So there's my biggest. When I say biggest, I mean highest degree. What's my highest degree term in the bottom? 3x to the third. So now to find the EBM for this whole thing, it's 2x squared divided by 3x cubed. Now I can't reduce 2 over 3. If it was 2 over 4, I would reduce those numbers. All right. So you can subtract the exponents. You have a 2 in the top, a 3 in the bottom. And if you subtract 2 minus 3, what do you get? Negative 1. But we don't like to think of things as having negative exponents. So if negative exponents kind of confuse you, think of it this way. It's 2 times x over 3 times x times x times x. How many x's can I cancel out of both the top and the bottom? 2. I can cancel 1 and 1, 2 and 2. Look where the x is left. I'm left with a single x and it's in the bottom. That's what a negative exponent means. You're left, this is how many you're left with. 1. That's where it is. Negative means bottom. 1 means 1 in the bottom. So 2 divided by 3x. That's your end behavior model. So now we can use that to find the horizontal asymptote. Okay, horizontal asymptote. What letter does it start with again? Y. Yep. Y equals. Now look at your end behavior model. 2 divided by 3x. And let x approach infinity. Remember, that's what this model is used for. What happens at the end? Infinity is at the end. So as x gets really, really big, what happens to what's in that box?
It's really, really small.
Really, really small. And it gets so small that it's approaching what number?
0.
0. Yep, it's approaching 0. Like if x was 1,000,000, it would be 2 divided by 3,000,000. Is it 0? No. If I had to give $2 to 3,000,000 people, does that mean everybody gets nothing? No. But it means everybody gets a very, 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 very small amount. 0.00001, something like that. Okay, so there's your EBM, and there's your horizontal asymptote. Okay, any questions on that one? Okay, let's try this one. Same directions. Find the EBM. And find the horizontal asymptote. And you always do it in that order. Get the EBM first, and then use that to get your horizontal asymptote. So Nick, what's my highest degree term in the top?
The 4th.
Okay, so the highest term has a degree 4. What's the whole term that has that degree?
2x.
Close. I'm not going to put 2x right here. I don't want to put 2x there.
Oh, just 2.
2 is going to be part of it. Can someone else tell me what else is going to go next to it? 2x to the 4th. So it's the entire term. 2, the x, and to the 4th power. How about my highest degree term in the bottom? 3x to the 4th. Again, I have a situation where 2 and 3 don't reduce. 2 over 4 would, but it doesn't here. And now, if you think of it like this, I usually don't write it out like this because I'm just used to doing it, but it kind of helps if you're not used to doing it. How many x's can we cancel from the top and the bottom? All of them. So all you're left with for an EBM is 2/3. So sometime an EBM has a letter in it, sometime it doesn't. Now, I'm going to ask this question. It's going to seem a little weird, but it's the same question I asked last time. Look at what's in the box. Let x get bigger and bigger. So look at the thing that's in the box, and as x gets bigger and bigger, what happens to the number in the box? Nothing. There is no x in the box. So if there's no x, as x gets bigger and bigger, it has no effect on this number at all. It just stays at 2/3. That's the answer for your horizontal asymptote. Y equals 2/3. This is the first time I think we've seen a horizontal asymptote that's not right on the axis. Maybe we saw one yesterday. I don't remember. Yeah, I think we did. But anyway, the asymptote is not on the axis. And notice the original problem. The degree in the top and the degree in the bottom were the same. Anytime the degrees are the same, the x's cancel out. And your asymptote is basically just dividing the two numbers in front. Anytime that the degree in the bottom is bigger than the top, you're always going to be left with a letter in the bottom. And that's always going to cause your horizontal asymptote to be at 0. anytime you're left with a letter in the bottom. So what we're going to look at is the case today where the degree in the numerator is either less than the degree of the denominator, like it was in part A, 2 is less than 3, or we're going to look at the case where the numerator is equal to the degree of the denominator. That's what we did in part B. 4 and 4, they were equal. So those are the kind of graphs we're going to try to sketch. All right, so there's a few different things that we have to do, and as long as we follow these steps, it doesn't make the graph too bad to figure out. We're going to use a combination of algebra and a graphing calculator. So the first step is, if you can, try to find your intercepts. Now, I'm going to put an asterisk there because that step, well, actually, you know what? I'll write if it applies. Because not every graph crosses the x-axis, not every graph crosses the y-axis. So if you have a graph that doesn't cross an axis, then you don't have an x-intercept or y-intercept. So try to find the intercepts if you can. Those are helpful points when you're making a sketch. Next thing you want to do is find your vertical asymptotes. That's usually pretty easy. We just have to find what would make the denominator 0. Worst case scenario, you're going to have to use quadratic formula. But most of the time, if it's not a really easy problem, it's probably going to be factorable. Now, what's the only time that you could have a number that makes the denominator 0, but you don't get an asymptote?
There's a common factor in the numerator and denominator.
Right. That's why it's a good idea to factor the numerator as well and see, do you have common factors? If you do, you have a hole in the graph, not an asymptote. Okay. After you get the vertical asymptote, we're going to get the horizontal. And the way we're going to do that is the way we just practiced in the notes. We're going to find the EBM. And now, at this point, we're going to have a bunch of dotted lines on our graph paper. So we'll have some asymptotes sketched. I want to see what happens near the asymptotes, especially the vertical ones. Because usually when you have a vertical asymptote, your graph does one of two things. As it approaches it, it heads up very high, or as you approach it, it kind of drops off and goes down very low. So we're going to check a value near the asymptote. When I say near, I mean really close. If the asymptote was 2, check what happens at 2.001. Check what happens at 1.999. Go very, very close to it and see what happens. You can't plug in the asymptote itself. You'll get an error. But you can go really, really close. And you're either going to get a huge positive number or a huge negative number. One of the two. And then after we do that, we can make our sketch. We should have a pretty good idea, and we can double check it by confirming with the calculator. Okay, so the real key, the most important thing here is steps 2 through 4. Find the asymptotes and check what happens near them, especially the verticals. Okay, so let's try to sketch that. It's x minus 1 divided by x squared minus x minus 6. Okay, I'll come back to intercepts. I don't always do these steps in this order. I usually do steps 2, 3, and 4 kind of together. And then if I feel like doing intercepts, I try to find those after. All right, if I want to find vertical asymptotes, what should we do to the bottom to make that easier to find the zeros? Yep. Turn it into what?
Could you turn it into like, well, because the x for 2x, so could you just put it together?
No, there's no like terms you can combine because one is squared and one is not. So we can't combine them, but we can rewrite what we have in a different way with parentheses.
You're gonna factor?
We're going to factor it. So this is going to factor as x and x. Two numbers that multiply to give me 6 and subtract to give me 1? Sure. 3 and, yeah.
I was going to say 2 and 3.
2 and 3, yep. So I'm going to put 2 and 3, and my signs are one of each. Which number do I want positive?
2.
The 2. And the 3, negative. Let's check it. Minus 3x plus 2x minus 1x. Perfect. So now I can write my vertical asymptotes. They're definitely not wholes. X minus 1 does not appear in the top and the bottom. So there's no common factors. Okay, what's one value that would give me a vertical asymptote? 3? Yep. And? Negative 2. So what I'm going to do now, I'm going to stop for a second and just put those on my graph. Let's put a dotted line at 3 and negative 2. Okay, I have graph paper too. I mean, if you wanted to do it on graph paper, and then you could just tape it in your notebook if you want one. Does anybody want a piece of graph paper? Yeah, sure. Let's just move that over. Okay, that's close enough. Okay. All right, so I got my vertical asymptotes. Now let's find the EBM, and that'll give me my horizontals. EBM. To find the EBM, it's actually better to go back to the original problem because you want to be able to see the highest degree term. You can't see that unless it's all foiled out. There's the highest degree term in the top. There's the highest degree term in the bottom. X over x squared. What does that reduce to when I cancel out the x's that I can?
1 over x.
It reduces to 1 over x. Yep. So now, my horizontal asymptote, let 0 get really big in 1 over x. What happens to the fraction 1 over x as x gets really, really big?
It gets really small.
And it approaches what number?
0.
0. So I have a horizontal asymptote at 0. So now I've got 6 sections. If you look at just the green, we're going to end up drawing in 3 of them. That's usually how this kind of graph looks. All right, so I've got those. So we did steps 2, 3. Let's check a value near the asymptotes. Now, I could do that by hand. Like if I wanted to plug in a value near 3, I could plug 2.99 in for x and do it all out. But it's a lot easier to use the table. It's just faster. So I'm not using the calculator for the graph yet. I'm just using it to look at the table. X squared minus x minus 6. Okay, so let's start with negative 2. What's a number that's very, very close to negative 2, but just a little smaller? A little bit to the left.
Negative 2.01.
Yeah, sure, negative 2.01. You can't plug in negative 2. You're going to get an error. That's an asymptote, but you can go really close to it. And if you go just to the left of negative 2, your graph is way down. It's at negative 60. Okay, if you go even closer, it's even further down, negative 6,000. You can't even see all the decimals I typed in. So just to the left of negative 2, the graph, I know that's not negative 6,000, but let's pretend. It's way down. All right. Now we're going to check a point just to the right. So what's a number that's just a little bigger than negative 2? Oh, negative
1.
Not that, I want to be really close to -2. Like extremely close, like within like 1/100th of the number -2. Understand?
Like negative 1.99?
Yeah, -1.99. So if I go to the right of -2, notice all of a sudden my graph is way, way up. Way up here. All right. Now let's check the other asymptote. 3. What's a number just a little bit smaller than 3? How about Michael?
2.99.
Sure, 2.99. If I go a little bit smaller than 3, if you go even closer, you'll notice it even more. If you go just a little less than 3, you're way down, -4,000. Okay, so it looks good. And now a number just to the right of 3, 3.001. Just after 3, my graph is way up at 400. Now, I know I'm approaching 0 as I head further left and right. Let's just try a big number and make sure that works. So 25 is 0.04. I meant to do 100. 0.01. 5,000. 0.000002. So it's very, very small, but it's still a positive number. So as you head further to the right, it's very, very small, but just barely positive. As you head further to the left, very, very, very small again, but just barely negative. So it's very, very close to this line, but just under it. Okay. So now, we could draw most of it, but I'm still not 100% sure what's happening in the middle. So for that, I'm not gonna worry about my intercepts. They might be helpful. All right, let's find the intercepts. So the y-intercept, that's when you plug in 0 for x. That's how you find the y-intercept. So the y-intercept is going to be 0, comma, something. Right? Let's plug in 0 and see what we get. If you plug 0 in the top, what do you get? -1. And if you plug 0 in the bottom, what do you get? -6. So your y-intercept is -1 over -6, or 1/6. So just a little above the origin, it crosses the y-axis. X-intercept. You do exactly the opposite. Now you plug 0 in on the other side. Plug it in for y. So this is y, right here. So put 0 in right there. If you do that, you would have a fraction equal to 0. What's the only way that a fraction can equal 0? Think about when you do division, how do you get an answer of 0? Yeah.
When 0 is divided by something.
When 0 is divided by something. So when 0 is in the top. So if you want to make a fraction equal to 0, which is what we want y to be 0, all that has to happen is the top is 0. What value of x would make the top 0? 1. No. So this is going to cross the x-axis at 1, 0. And I think that's enough points. So now, we're going to sketch it, and you have to remember to stay close to the dotted lines. You can never cross them. So you're going to have something kind of like that, getting closer and closer, but never touching it. And the same thing here. Getting closer and closer and closer, but never touching it. Now those have to connect. Everything about these graphs are curved. So the only way they can connect is if I go like this, and I say, you know what, I just want to keep heading right, but I can't. I'm running into a dotted line. Look at that dotted line, it's like a brick wall. You can't cross it. So what happens is, as I start heading towards it, I have to bend down. I have no other choice. It should probably look a little smoother, but it's as good as I can do. So it has to curve. Same thing's going to happen in the upper right section. These two dots have to connect. So I have to stay along the asymptote. That's how asymptotes work. Stay along it, but then all of a sudden, you're hitting a brick wall. Causes you to curve up. It's not the smoothest looking curve, but whatever. Now, in the middle, I have a point way up here. So I know I have to stay near that asymptote, and I know I have to stay near that one. And I got to go through those 2 points in the middle. So stay near the asymptote until you start getting to the middle, and then it's going to have to curve, and it wants to keep going right, but it can't. It's hitting a wall, right? It has to go and stop, and then go down. And that's what the graph looks like. So you'll never cross the vertical asymptotes. In the middle section, you might cross the horizontal. Okay, let's hit graph and we'll see how we did. All right, not too bad. So we got the 3 sections, the 2 that curve here and the one that has that kind of S shape in the middle. Looks like theirs is a little flatter in the middle. Mine maybe should be a little flatter, but honestly, that's fine. That's a good graph. Okay, so any questions on that? Yeah.
Yeah, I kind of zoned out for a second. More my calculator wasn't working. How did you get the further up dots on each side?
That's when I tested a point like 2.99 and 3.01.
Okay, so you tested a point on both sides.
Yep, on both sides of each asymptote.
Okay, so how come with the one all the way to the right, there's one on top of there's one on the bottom of it?
That's when I tested one. That's when I did this one.
Yeah.
And this one. That's when I said, well, let's plug in a really big number for x. Like, watch what happens. If x heads further and further to the right, it gets very small, but it's still positive.
Okay.
So that's a very, very small number, but it's still a little above 0. And then as you head further to the left, it's a very, very small number. So it should be super close to that green line, but it's negative, so it's a little below. That's how we got those. All right, so let's try, we'll try one more of those, and this will be our last one. So the last problem we did, the degree in the top was a 1, degree in the bottom was a 2. So the degree in the top was smaller. Now they're equal. Okay, I already kind of wrote out all the things you need to find. So let's start with the vertical asymptote. Okay, just like last time, what should I do to the bottom to make the vertical asymptote easier to find? Factoring. This time it's not as complicated of a factoring. You only have 2 terms, so all you can do is pull out what they have in common. What do both of those terms have in common? X. So all you can do is take out an x, and you're left with a 2x minus 5. That's all you can do. I'm not even going to rewrite the top. I don't even care about the top. Just keep the top the same. So now I have 2 factors. 1, 2. What would you plug in for x to make the first factor 0? 0. Don't think too hard on that one. It's just 0. Now the second one, what would you plug in for x there to make that one 0? Yeah, 2.5. Because if you take 2 times 2.5, that's 5. 5 take away 5 is 0. Right? So 2.5, I think it's, if you're graphing, it's definitely nice to have decimals. If you wrote 5 halves, that's okay too. So there's your verticals. Let's do all the work first. Horizontals. Well, I really need the EBM first. Rebecca, what's the highest degree term in the top?
3x squared.
And the highest degree term in the bottom?
2x squared.
And when you divide, what happens to the x's?
They cancel out.
They cancel out. So my EBM is just 3 over 2. There's no x in it. So now, if you look at what I have the box around for the EBM, let x get really big in that box. What happens to the fraction 3 over 2? Stays 3 over 2. So there's your horizontal. Now I'm at the point I want to graph all those asymptotes and then use my calculator to check some points. Then I can make my sketch. So I've got one at 0 and 2.5. Okay, and when I say check some points, I'll also look at the intercepts as well. So 0 and 2.5. So there's 0, close enough, and 2.5. Horizontal, 3 halves. Well, 3 divided by 2, that's about 1.5. I'm going to fix that one though. Okay, I got my 6 sections again. We're going to end up drawing in 3 of them. It's going to look very much like the last graph. The only difference is now the horizontal asymptote is not on the axis. It's been pushed up. All right, so now I've got to type all this in. We've got 3x squared plus x minus 4. 3x squared plus x minus 4 divided by 2x squared minus 5x. Okay, my first asymptote was at 0. What's a number just a little smaller than 0? Pretty close to it. Is it up? A number very close to 0, but a little smaller? Okay, that's a little bigger. I'll do that one next. Can you give me just the one that's a little smaller?
Oh, negative 1.
Negative 1?
20.
I like what you said the first time because it was really, really close. Can anyone give me one that's just as close as the first one she said, but smaller? Yep.
Negative 0.001.
Yeah, let's go negative 0.001. We're down at negative 800. So if we go a little smaller than 0, we're way far down. If we go a little bigger than 0, we're way up, 800. That usually happens. One side's down, one side's up. All right. Next asymptote is 2.5. What's the number just a little smaller than 2.5?
2.49.
Sure, 2.49. Negative 300. So when you're just before 2.5, you're way down. Just after 2.5, you're way up, 346. Now, I like to just check what happens as I head really far right and left. If I pick a number really far to the right, like 100, it's getting closer to that asymptote, 3 over 2, but it's staying above it. Okay, if I go to 500, 1.509. It's still above 1.5. So it's just above, but it's getting super close to it. If I head far to the left, negative 500, 1.49. It's getting very close to 3 over 2, but it's just under it, okay, 1.49. Okay, so I've got enough information to sketch what's happening here. Well, I know it's going to look something like that. I'm not exactly sure the curve yet. And that's going to come up. I'm going to figure out where it crosses the axis, and that'll give me a little bit better picture. So the x-intercept, or actually, let's do the y-intercept. Plug 0 in for x. What happens in the top if you plug 0 in for x, you get 0 plus 0 minus 4. That's okay, negative 4. What happens if you plug 0 in for x in the bottom?
You get 0.
you get 0. And is that okay? No. 0 was a vertical asymptote. You can't plug 0 in. So what that means, there is no y-intercept. This graph never crosses the y-axis. Okay, x-intercept. Let's try that. That's when we plug 0 in right here. So the only way that a fraction can equal 0 is if the top equals 0. Well, that's a quadratic. It probably at this point would be a little easier if we factor the top. It does factor into 3x and x, and two numbers that multiply to give me 4. You've got 2 and 2, and 4 and 1. I would go with the 4 and the 1. Because 3 times 1 is 3, 4 times 1 is 4, 3 take away 4, I can get a 1 in there somehow. So now I just have to decide on my signs. Let's try plus, minus. So that gives me 3x times -1, 4 times x, -3 plus 4, +1. Perfect. So there's actually two numbers you could plug in to make the top 0. What's one number you could plug in to make the top 0? 1. So you could plug in 1. So this is going to cross the x-intercept at 1, 0. So that's your x-axis. And what about the other factor? What would you plug in for x there? Just think of it like this. Yeah.
-1 and 1/3.
-1 and 1/3. Yeah, -4/3. So I wasn't exactly sure where it was going to cross the axis. It's going to cross at -1 1/3. So my graph is going to look something like that in that section. In the middle, I've got to connect all 3 dots. It's going to be pretty steep because the middle is very skinny. So it's going to have to look something like this. That's the best I can do. In fact, that's so steep that if you try to graph it on the calculator, I don't think it will.
Oh yeah, on the calculator it looks all broken up.
Yeah. What happens is when things get too steep on the calculator, it just says I can't do it, and it just doesn't even try.
Can you blame it?
So this part should keep going down. This part should keep going up. So that's how you sketch rational functions. Okay, most of it is just checking points on the table. Okay, so homework tonight is 1 through 5 odd, 9, 11, 15, 17 to 22. 23 to 25, and 29 and 33. Not every question is graphing. There are some, but I think one sheet of graph paper should be plenty. If you want another one, go ahead.